In this video, we'll be talking about how do we find the area between two curves with respect to y. So basically, the area between two curves can be found with respect to x or with respect to y. There's another video in this playlist that will go over with respect to x if you need to visit that. So when we find area with respect to x, the function should be in a y equals format. And when found with respect to x, the bounds of the integral are x values. Whereas when we do with respect to y, basically we're going to have all these opposites here. So they should be in an x equals format, basically in terms of y. And the bounds, therefore, are going to be y values. So first, what we're going to do in this video is just practice setting up integrals with respect to y, just so we get that idea. And then we'll talk about, okay, actually evaluating it using our calculator. All right, so let's look at this practice question. So this practice question is kind of a follow-up to already learning how to write integrals to express area with respect to x. And then we'll talk about how everything has to change in part C when we do it with respect to y. All right, so first what we're going to do for part A is we're going to find the points of intersection. I can see from the graph that those are -2, 5, and 3, 0. We could also get those intersection points by setting the functions equal to one another when they're in y equals format or using substitution. We could also solve for y, put them in the y equals of our calculator, and find intersections that way. But since I have their graph right here, I can see those values clearly from the picture, so we have point A complete. Now B says, write but do not solve an integral that would determine the area bounded by the two functions with respect to x. So if we're doing it with respect to x, let me just scroll up here for a second again. That means that we need the functions in a y equals format, and we also need the bounds to be x values. So I know already the bounds are going to be -2 and 3. I found those x values in part A. But if I actually look at our functions here, they are both not in terms of y. So what I'm going to do is I'm going to rewrite x equals -y plus 3. If I add the y to the other side and then get y by itself, I'll have y equals 3 minus x. So now when I go and do part B, I'm going to be using y equals -x squared plus 9 and y equals 3 minus x. When I look at the graph, the upper function is the parabola, so that's the -x squared plus 9. We're going to subtract the lower function and dx. So that would be our integral to represent that area with respect to x. When we are doing it with respect to y, sometimes the problem can get a bit more complicated. So what we're going to do is we're going to look at this and we're going to talk about if I have this graph here, almost as if I'm turning my paper or turning my head. So I want this, I'm going to highlight here for a second. I want this piece to essentially be the upper function. If you're holding your paper straight on, we could say that that's the right function. If you turn your head to make it similar to what we did on part B, you could call that the upper function. That would mean that over here is a lower function. But what's going to make this problem a little tricky is that we have another lower function. So let's talk about this in terms of right versus left. So let's imagine that our paper, we're looking at it straight on. And I'm going to just draw this little divider in here. When I look at the top piece of this, this is the right function. This is the left. When I look below that little line that I drew at 5, this is my right function. This is my left. So what we have to do here, if you've already watched my video on multiple intersections, we're going to be doing something similar here. We're going to be breaking this shaded region up into two smaller shaded regions. And the reason that we're going to do that is because when we look at this, the right function is always the same, but the left function is changing. Or if you turned your head, like I said, or you turned your paper, the top function, the upper function is always the same, but the bottom one is not, okay? All right, so what I'm going to do is I want all of these functions now in terms of y, which means they're going to be in an x equals format. Now, over here, where this left function is in green, the problem already gave us that in an x equals format, and it told us, and I'll zoom out in a second, that that was x equals -y plus 3. But I have to find the blue and the pink function here. So if I zoom out, that other function was y equals -x squared plus 9. Let's solve that now for x. So I'm going to subtract the 9 over. I'm going to divide out that negative. and I'm going to take the square root. When I do that, I'm going to get plus or minus the square root of negative y plus 9, or you could have 9 minus y is equal to x. So if I go over to my graph, the positive version is what we have in blue here. The negative version is what we have in pink. And now we can use that to set up our integrals. So I'm going to just zoom out a bit so we can see part C here and see me fill it in. So let's talk about this section first that I'm going to shade in right here in pink. So if I look at that section, the bounds of that section in terms of y values, so with respect to y, our bounds are y values, that section goes from 0 to 5. We're going to do right function minus left, so the right function is the square root of negative y plus 9. The left function, I'm going to put in parentheses, or you could distribute that negative, is negative y plus 3 dy. Then we're going to add on now this section that I'm shading in blue here. So when I do that here, my integral is now going to go from 5 to 9, because those are the bounds, the y values for that section. Then it's going to be my right function, so positive square root of negative y plus 9 minus the left function, which is the negative version. Okay, you could change that double negative in there if you'd like, dy, and that would be our integral or integrals that represent the area of the shaded region with respect to y. Now, if we were to actually calculate part B and C, we would get equivalent answers. We're finding the area of the same exact section, the same region. It's just one's in terms of x and one's in terms of y. Let's try another one where we're simply just setting up integrals, but this one you'll see is a little bit better. So if I take a look at this one, it says write but do not solve an integral that would determine the area bounded by y equals ln of x and y equals negative x plus 3 with respect to y. All right, well, I notice if I'm going to do this with respect to y, I need these in x equals format. So what I'm going to do, I'm going to put e as the base on both sides. So I have here e to the y is equal to x. And over here, I want x by itself. So if I add x to the other side and then subtract the y over, I have x equals 3 minus y. All right, so if I go over to my picture, I can tell that the line over here is basically x equals 3 minus y. And I can tell that this curve is x equals e to the y. And what we're going to need to do is we're going to have to determine what this point of intersection is. All right, if we take a look at the right of my screen here, what I've done is basically I've put these two functions in the y equals of my calculator, graphed them, and I've already gone ahead and found that point of intersection. So looking over here, I can tell from my calculator that this point is 2.20794, 0.79206. Now, since this problem is respect to y, when we're creating our bounds, we really need to be using the y value. All right, so let's actually set up our integral. So our bounds are going to be from 0 to that y value of the point of intersection, so 0.79206. And we're going to do right function minus left function. So if I slide back over to the graph, unlike the previous problem that was a little more complicated, I can see here that the right function is always the linear part. The left function is always the natural log graph, or in this case exponential now that we're in terms of y. So I don't have to set up two integrals here. So we're going to do 3 minus y, the right function, minus the left function, which is e to the y, dy, and that would be our setup for the integral for that area. Okay, number 3, we're going to find the area bounded by f of x equals 3 minus x, g of x equals 1/2 x plus 3, and x equals 3 with respect to y. So the first thing I know is I need these to all be x equals. So I'm going to take these two functions. I'm going to put y in for f of x and g of x. And what I'm going to do is I'm going to solve for x in both cases. So over here I have x is equal to 3 minus y. I move the x over, and then move the y back to the other side. Over here, I'm going to subtract the 3 over, and then I'm going to multiply everything by 2 in order to get rid of that fraction. So I have x equals 3 minus y as the first, and x equals 2y minus 6 as the second. All right, so let's label these on the graph and maybe color code a little bit to keep track of it. So f of x equals 3 minus x, or the x is equal to 3 minus y. I know that that's the line that has the negative slope. And then g of x is being 1/2 x plus 3, I know is the line with the positive slope. Now I do have a third line here, which is the vertical line x equals 3. And when we look at this problem, if you've been following along in this video, this is similar to number 1, where if I turn my head and look at this, I can see, or even if I look at it head on, I can see that the function that's on the bottom or left, however you're looking at it, is changing here. So what I'm going to do is I'm going to actually draw a little divider. And if you look at that top section, the green line, the green graph is on the right, the blue is on the left. Whereas if I look below this line, green is on the right, but pink is on the left. So what I'm going to do is I'm going to label all of these. So the green is x equals 3. Over here, the blue was x equals 2y minus 6. And the pink was x equals 3 minus y. So I'm going to set up 2 integrals and add them together in order to represent this area. So let's start with the bottom region, this part that I'm scribbling in right now. The y values go from 0 to 3, so those are my first set of bounds. The right function is 3, or the right equation, I should say in this case. And then I'm going to subtract out the line, so 3 minus y dy. And then I'm going to basically do that same idea, but for that top section. So the top section, the bounds, we are going from 3, and the upper bound is 4.5 there. We're going to do 3 minus 2y minus 6 in this case, dy. Okay, if you look at the right hand of my screen, I have now evaluated these integrals in the calculator. So this is 4.5 plus 2.25. And together that would make my area 6.75. Now just a note on this one, if we take a look at this, what we're really finding here is area of a triangle, or 2 triangles if we think about it separately. So yes, in order to find the area with respect to y, and using calculus, this is the work we would need to show. But we should be able to say that this whole entire figure, like this initial picture, is a triangle, and use 1/2 base times height in order to verify our answer. So again, we have to show the calculus behind it, but since we notice that this is an actual shape that we know how to find the area of from geometry, we could verify our answer that way. Okay, for our last question here, it says, let R be the region bounded by x equals 2y and x equals radical y, and find the area of R. So notice something here, that there is no graph on this one. So in order to find points of intersection, I can use the calculator, assuming I have access to it, or I could also just set these pieces equal. So I'm going to show the algebraic work here, since we've been using the calculator a lot in this video. So if I set these 2 functions or 2 equations equal to one another, and I solve, so if I square both sides here, get everything on one side, I could factor, and I got y equals 0 and y equals 1/4. Now I know what the bounds of the region are. Now when we look at this, we might not know which one is the upper function. So if you look and you peek at the graph on the right of my screen, I can see here that the square root function is the upper one and the line is the lower function. But if we didn't know that, we could do a couple of different things to kind of take that into account. Okay, so I've gotten rid of the graph here. Let's pretend that we don't know which is the upper function and which is the lower. What I could do here is basically say, all right, we know y equals 0 and y equals 1/4 are the points of intersection. If I plug those values back into these equations to figure out the x values, I could get an actual point of intersection. And when I do that here, I'm going to change this to 0.25. I get 0, 0, and 0.5, 0.25. So we could kind of pick a test value between those x coordinates. So like, let's say that I picked, I don't know, 0.25 again. If I now plug in, and this is for x, if I plug 0.25 into each of the functions, I could solve for y, and I'm going to see that this is going to give me a higher value. This is going to give me a lower value. And now I know which one's the higher or the upper function. So that's one option. Let's say we were doing that option, and I know now that radical y is the upper. I know 2y is the lower, dy. That would basically give me my area. If I didn't know that, what I could do as just kind of like a workaround is I could put absolute values around this. So if you think about it, like 3 minus 2 is 1. 2 minus 3 is negative 1. But if we know we want that answer to be positive, if I had stuck absolute value bars around 2 minus 3, I would get that positive value back. So that's another workaround that you could do if you do not have the graph available to you. Okay, so if you take a look at the right-hand side of my screen here at the calculator, you'll see that I typed both of them in, one without the absolute value bars because I did know and I tested to figure out which one is going to be the upper function, and then one with like our workaround with the absolute value bars. And you can see here in this case that I am getting the same answer. So our answer to this question is to 3 decimal places 0.020 or 0.021 if you are rounding.